So here is some always, sometimes, never practice. Just what you guys wanted, right? If a segment bisects the vertex angle of an, you should try these first yourself. If a segment remember, sketch a diagram. If a segment bisects the vertex angle of an isosceles triangle. So if this is isosceles, that means you have that. There's a vertex angle. It says it bisects what? Bisects that vertex angle. Well, these two triangles are congruent by SAS, right? And if these two triangles are congruent, that means these pieces down here are congruent by CPCTC, which means this thing is a median. So this is always. Now, let's look at this next one. If a segment, this is the same diagram, if a segment bisects the vertex angle of an isosceles triangle, you're going to have the same situation where these two triangles are congruent. Now, this next thing kind of involves something that we're going to do in the next chapter, but you can still intuitively see it. If these two triangles are congruent, that means these two angles are congruent, right? But we also know that these two angles are supplementary. Well, if angles are congruent and supplementary, don't they have to be right angles? Yeah, they do, don't they? So that thing would be an altitude, always. Okay, the next one. If a segment is an altitude of an isosceles triangle, then the segment is also a median. Well, if you look at how I drew it here, then, well, hold on. Let me go right here. It says if a segment is an altitude of an isosceles triangle. So if this triangle is isosceles because of that, and then we draw in the altitude, remember, because this triangle is isosceles, you're going to have these base angles congruent too. So these two triangles would be congruent by angle, side. So then it is a median, that's true, but there's a big but here. We didn't necessarily have to draw it this way. What happens if it just said if a segment is an altitude of an isosceles triangle? Well, that altitude could be to the leg. You see? Is that altitude? It doesn't say it has to be from the vertex angle. Clearly there, it's not going to work. So this would be sometimes. Okay, I'm going to let you guys mess with the other ones. These are angle, side. It's good practice, though. Okay. Sorry, I said angle, side. This is always, sometimes. If you guys noticed on your reason sheet, back in the front when we first talked about proving triangles congruent, there was, I think it might have been listed a fifth way there, which we haven't talked about, and that's called RHL, okay? Or sometimes I just call it HL. RHL or HL, just realize it's the same thing. It stands for hypotenuse leg. So the R stands for right angle, hypotenuse, leg. Now, what this is this is really, this thing might disappear for a second. Let's see if it does. Yep. It'll come back, I think. What this is SSA. Now, when we talked about that earlier in the year, SSA, we decided it's not true. But this is a unique situation where you have a right angle. So again, if I have a right angle and a leg congruent, so let's say boom, boom, and let's say this leg is congruent and the hypotenuse is congruent. So I'm going to have some kind of hypotenuse. Well, the only way I could create that right triangle if these are congruent. These triangles would be congruent. Because if I we're told we have to have a right angle, so that's got to be a right angle in the corner. We're told that a leg's congruent, so I got that. And the hypotenuse is congruent. If I swing this hypotenuse up to the, then I'm not going to make a triangle anymore. For me to make a triangle, I have to extend it. Well, then the hypotenuse wouldn't be congruent. So this is another way of proving triangles congruent through RHL or HL. This is the last way of proving them congruent. Here, let's do a proof. CE congruent to DF, BC congruent to GF. Hey, I think I can do something with those two little triangles on the corners. First, I'm going to say that CD is congruent to EF if the same segment is subtracted from congruent segments, then the differences are congruent. Now, I now have to say that angle BDC and angle GEF are right angles. If lines perpendicular, then intersect at right angles. Okay, now this is nice. If you look ahead, then how are you going to prove these triangles congruent? You have a right angle. You have CD congruent to EF. You're given BC and GF, which those are the hypotenuse. You know you're going to use HL or RHL. There is no need to say that the right angles are. There's no need to say that the right angles are congruent when you're going to use RHL. So we can bypass that step. We can go to, it's kind of built into RHL. As long as you've said that you have right angles, you're okay. Okay. And the next thing, of course, what do I have to prove? I have to prove that the whole thing's isosceles. I'm going to take angle C congruent to angle F, and that's by CPCTC. And lastly, we can then say that triangle ACF is isosceles. If angles, then you have an isosceles triangle. Okay. On the back side, we're going to do just a couple of these. And then I'll leave one to you. So here, circle O. Make sure you pay attention. A lot of times people go too fast and they don't pay attention to the perpendicularity. It says YO is perpendicular to YX. ZO is perpendicular to ZX. So the right angles, whoops, disappearing ink. We have angle OYX, comma, XZO, right angles. If lines perpendicular, then intersect at right angles. So remember, we have radii here, right? OY congruent to OZ. All radii of same circle congruent. We now have a reflexive piece, and that is OX congruent to OX. So I have triangle YOX congruent to triangle ZOX by RHL. So I didn't have to say that the right angles were congruent. And now I can say YX is congruent to ZX by that. Okay, so down here, now look, ABC, watch this. ABC and ADC are right angles. With what we just learned, we could prove these triangles congruent in just 3 steps, right? Because we're already told right angles, we're told this, we say this reflexive step, and then we're done. That would be too boring. You guys are too good for that. So what I want you to do is I want you to try to prove this, do this proof without using HL, without using RHL. It can be done. You should pause this, stop, and give it a try yourself. Okay. Check this out. Draw DB. 2 points, determine a line. Hey, look at that. Turn it sideways if it helps you see it. Remember, this we just created an isosceles triangle. So now angle ADB is congruent to angle ABD from if sides then angles. I had those right angles, so I'm going to say angle ADC is congruent to angle ABC. If angles right angles, then congruent. Hopefully you see where I'm going with this. Now I can do some subtraction, right? I can say the angle CDB is congruent to angle CBD from subtraction, right? If congruent angles subtracted from, if congruent angles subtracted from congruent angles, then the differences are congruent. And if we have this angle congruent to this angle, now look at this triangle here. We can say if angles, then sides. And we can now prove those big triangles congruent. Don't need the reflexive step because we can prove it by SAS. So that was kind of neat. All right. So we kind of just proved the HL theorem, HL postulate right there. Kind of neat. Anyway, I'm going to leave the last one to you. You can check on Canvas with my solutions. I had 7 steps for this one.